right? That always means we charge the plates. So there we go. Did you see it? I didn't see it because I had to concentrate. Did it go like this? Good. So now it's charged. We don't take this connection off. It's connected with the power supply all the time. And now I'm going to open up. And as I'm going to open up, the potential remains the same. So this voltmeter doesn't give a damn. It will stay exactly where it is because 1500 volts remains 1500 volts. But now, as we open up, we're going to take charge off the plates, and so this I expect to go to the left. Every time that I give it a little jerk, I do it now, it went to the left. I go it now again, I go to 2 millimeter, go to 3 millimeter, go to 4 millimeter, make it 5 millimeter, 5 millimeters, 6 millimeter, and I finally end up at 7 millimeters. And every time that I made it larger, you saw the hand go to the left. Every time I took some charge off. So that is demonstration number 3. Why did I go to 7 millimeters? You've guessed it. Now I want to plunge in the dielectric. So my experiment number 4, I start with 1500 volts. I start with D equals 7 millimeters. And I'm not going to change that. There's no dielectric in place, but now I put the dielectric in. So kappa goes in. What now is going to happen? Well, for sure, V is unchanged because it's connected with the power supply. So that cannot change. What happens with Q3? Look at this equation. When I put in the dielectric, I know that the capacitance goes up by a factor of kappa. C will go up by a factor of kappa. If C goes up with a factor of kappa, and if V is not changing, then Q3 must go up by a factor of kappa. Follows immediately from equation 3. So this must go up by a factor of kappa. What does that mean? That charge will flow to the plates. I increase the charge on the plates, and so my ammeter will tell me that. And so my ammeter will say, aha, I have to put charge on the plates, and so my ammeter will now do this. And that's what I want to show you. The remarkable thing now is that the electric field E, the net electric field E, will not change. And you may say, but you put in a dielectric. Yeah, I put in a dielectric, but I kept the potential difference constant, and I kept the D constant. And since V is always E times D, if I keep this at 1500 volts, and I keep the 7 millimeters, then the net electric field cannot change. It's exactly what it was before. That is the reason why Q3 has to change. Think about that. Because you do introduce induced charges on the dielectric. And you have to compensate for that to keep the E field constant. And the only way that nature can compensate for that is to increase the charge on the plates, the free charge. And so that's what I want to show you now, which is the last part. So I'm going now to put in the dielectric. And what you will see then is that current will flow onto the plates. So the propeller will do nothing. Will sit there, and you will see this one go clunk when I bring in the glass. And then it goes back, of course. There's only a little charge that comes off, and then it will go back. So as I plunge it in, you will see charge flowing onto the plates. There we go. You ready for it? 3, 2, 1, 0. And you saw charge flowing onto the plates. When I remove the glass, of course, then the charge goes off the plates again. You see that now. I've shown you 4 demonstrations. None of this is intuitive. Not for you, and not for me. Whenever I do these things, I have to very carefully sit down and think what actually is changing and what is not changing. I have no gut feeling for that. There is not something in me that says, oh yes, of course that's going to happen. Not at all. And I don't expect that from you either. The only advice I have for you, when you're dealing with these cases whereby dielectric goes in, dielectric goes out, plates separate, plates not separate, power supply connected, power supply not connected, approach it in a very cold-blooded way, the real classic MIT way, very cold-blooded. Think about what is not changing, and then pick it up from there and see what the consequences would be. How can I build a very large capacitor, one that has a very large capacitance? Well, capacitance, C, is the area times epsilon 0 divided by D times kappa, which your book calls K. So make K large, make A large, and make D as small as you possibly can. Yeah, but you have a limit for D. If you make D too small, you may get sparks between the conductors, because you may exceed the electric field, the breakdown electric field. So you must always stay below that breakdown field, which in air would be 3 million volts per meter. If you want a very large kappa, you would say, well, why don't you make the layer water in between? That has a kappa of 80. The problem is that water has a very low breakdown electric field, so you don't want water. If you take polyethylene, I just call it poly here, just as abbreviation. Polyethylene has a breakdown electric field of 18 million volts per meter, and it has a kappa, I believe, of 3. Many capacitors are made whereby the layer in between is polyethylene. Although mica would be really superior, be it as it may, I want to evaluate now with you two capacitors which each have the same capacitance of 100 microfarad. But one of them, the manufacturer says that you could put a maximum potential difference of 4,000 volts over it. That's this baby. And the other, I go to Radio Shack, and it says you cannot exceed the potential difference not more than 40 volts. Well, if I have polyethylene in between the layers of the conductors, then I can calculate what the thickness D should be before I get breakdown. That's very easy, because V equals ED, and so I put in here 18 million volts per meter, and I go to 4,000 volts, and then I see what I am with D. And it turns out that the minimum value for D, you cannot go any thinner, is then 220 microns, and so for this one, it is only 2.2 microns. You can make it much thinner, because the potential difference is 100 times lower. So you can make the layer 100 times thinner before you get electric breakdown. I want the two capacitors to have the same